Magnetic fields. So we're going to look at magnetic field lines and the force that magnetic fields will place on electrically charged objects. So first of all, once again we get back to this idea that there are only magnetic dipoles. With the electric field, it started at a positive charge and then it ended at a negative charge. Notice that the electric field lines, the magnetic field lines inside a magnet are actually connected back on themselves. Okay? We don't have an exact pinpoint where you could say, well, this is the North Pole, this is the South Pole. The North Pole actually represents where the magnetic field lines are leaving the magnet. The South Pole represents where the magnetic field lines are reconnecting with the magnet. But within the magnet, again, the field lines make a complete circuit. So once again, there are no magnetic monopoles from which these magnetic field lines will emanate. We use B to symbolize the magnetic field. And again, if we think about the direction that the magnetic field lines point, they point in a direction that a north pole will experience a force in. So again, north and south poles can't be separated. So really what happens here is, with these magnetic field lines, on a magnet, they will pull on the north pole and they will repel the south pole. Again, here we can see the difference between our magnetic field lines, which connect back on themselves always, and here we see the electric field lines, which start at a positive charge and terminate at a negative charge. So there are many parallels between our electric field and our magnetic field. However, again, this idea of field lines starting and stopping, okay, is not one that crosses over to the magnetic field lines. In a magnetic field, a magnetic monopole will orient itself such that the north pole will point in the direction of the field, or I should say, the north pole will align itself in the direction that the field is traveling. The south pole will align itself in the opposite direction. So really, placing a magnetic dipole within a magnetic field creates a torque rather than a net force. The north pole and south pole are being pulled with equal and opposite forces, but they're not entirely aligned, and this creates a torque. This is exactly the same thing that happens when we have an electric dipole placed in an electric field. The positive charge will be pulled in the direction of the field, whereas the negative charge will be pulled in the opposite direction, and this will create a torque, causing the dipole to try to align itself with the field. Again, we can visualize the magnetic field with a ferromagnetic material like iron filings. And again, you can see how the iron particles sort of orient themselves or congregate around these magnetic field lines and help you actually visualize what's going on. And again, you can actually see magnetic field lines within the magnet itself. Opposite poles attract, so north pole is attracted to a south pole. We could visualize the actual vectors themselves. We'd see the arrows pointing away from the north pole and toward the south pole. Like poles repel, again you can see the field lines come to a point where they actually asymptotically will go in the horizontal direction there. So again, when we have magnetic dipoles, they like to orient themselves with the magnetic field. But also, charged particles will feel a magnetic force as long as they're moving perpendicular or have a perpendicular component to the magnetic field line. So if you're an electric charge and you're not moving, there's no force. Okay? You can have as much magnetic field as you want. A static electric charge, it's not going to feel a force. If the electric charge is moving with the field lines, parallel to the field lines, again, there is no force on the charge. It is only when the charged particle has at least a small perpendicular component to the magnetic field that it's going to experience a force. So magnetic fields will put forces on magnetic dipoles, but they'll also put forces on moving electric charges. Here's the equation for the force on a charged object due to a magnetic field. Again, you can see that it depends on the charge of the particle that's moving, but it also depends on the velocity. So again, if the velocity is 0, there's no force. Finally, we have a vector product, what we call a cross product, between the velocity and the magnetic field. Now a dot product, okay, when you take a dot product, you're taking the product of the two scalar values of the vectors, and then you're multiplying it times cosine. In this case, you're taking the scalar values of each vector right here and multiplying it by sine of theta, where theta represents the angle between the two vectors. So if V and B are both in the same direction, theta is 0, and the sine of 0 is 0, there's no force. How do you maximize the force? Make these two vectors perpendicular, make these two vectors as large as possible, and the force will become maximized. Okay? Now, with the cross product, it's a little bit difficult here because when we create the cross product, the force itself is actually perpendicular to both vectors in the cross product. So if V is in the x direction and B is in the y direction, for instance, okay, there's only one perpendicular direction to those. V and B define a plane, and F has to be perpendicular to that plane, so actually it would be in the z direction. This makes dealing with charges moving in magnetic fields a little bit difficult because it involves three-dimensional visualization of what's going on. Okay? And again, we can simplify the magnitude of the force as being QVB, and again, theta represents the angle between our velocity vector and our magnetic field vector. Alright, let's do some of these problems. Alright, again, we can rewrite this equation. The strength of the magnetic field can be defined by the force it places on a charged particle divided by the charge of the particle times the velocity of the particle times sine theta. The units for a magnetic field are measured in flux per unit area. Webers are a unit of magnetic flux, or by newtons per coulomb times meters per second. Okay? It can also be expressed as newtons per amps divided by amps meters. This is basically the SI unit for the magnetic field. 1 Tesla, which is named after Nikolai Tesla, is a really, really large, intense magnetic field. Most of the time when we're dealing with magnetic fields, we would be dealing with magnetic fields much less than 1 Tesla. So again, Weber is magnetic flux. We'll talk about that more later on. The CGS unit for magnetic field is the Gauss, and 1 Tesla is equal to 10 to the 4 Gauss. So Gauss is a much smaller unit for magnetic field. Just some examples of magnetic field strengths and their associated magnetic fields in both Tesla and Gauss. The human brain, actually, due to the movement of ions, you get a flow of current here, but the movement of ions across different synapses, you get a magnetic field of 1 trillionth, or 10 to the minus 12 Teslas. In Gauss, that's 10 to the minus 8. For a magnetic tape recording, the recording head has a magnetic field to record information on that head, about 2.4 times 10 to the minus 5 Teslas. Okay? The Earth's magnetic field sorry about this, this 5 got knocked down here, is roughly about 5 times 10 to the minus 5 Tesla. Refrigerator magnet, about 5 millitesla. Sunspots, which block the flow of energy from the sun, creating a dark, cooler spot on the surface, is about 0.15 Teslas. Loudspeaker magnets, which are used in the driver of a speaker, 1 to 2.4 Teslas. Medical MRIs, they actually have to use superconducting magnets because not only is the magnetic field required to be quite high, you can only get this with superconducting magnets, the gradient of the magnetic field, how quickly it focuses down to a point, also has to be very high. That's only achievable with superconducting magnets. Again, high resolution MRI is going to be about 9.4 Teslas. So as with everything, higher quality imagery really requires more intense magnetic fields. NMR spectrometer, which is used to analyze molecular bonds, actually looks at the nucleus, and from the environment of the nucleus we can determine different aspects about bonds. Between 10 to 24 Tesla. The best superconducting magnets that we can really make in the lab are about 45 Tesla. Pulsed magnets can be achieved by sending a large current for a short amount of time, but we can only do this for a short amount of time because what happens is the material gets very hot, and either if it's a superconductor it becomes non-superconducting, or if it's made out of copper, the copper would melt if the current was continuous. Neutron stars have some of the strongest magnetic fields, about 1 million to about 1/10 of a billion Tesla, and magnetars, which are extremely strong neutron stars, actually are even stronger than that, up to 1/10 of a trillion Teslas. So back to the magnetic force on a charged particle. Let's say we have this positive charge right here, and we want to determine, given a magnetic field going in this direction, where the force is going. We use something called the right-hand rule. Okay, and obviously you're going to have to use your right hand for this. If you're left-handed, well, you're being discriminated against. But you use your right hand, and it goes like this. The force, okay, is V cross B. So we put our fingers in the direction of the velocity. We then curl our fingers or our single finger in the direction of the magnetic field, and the force points in the direction that our thumb goes if we stick our thumb out. So V cross B, using the right hand rule, going backward this way, gives us a force in this direction. So again, this is really one of the biggest challenges for this course, is actually determining the direction of the force, or determining the other vectors based on two of the knowns. It requires you to think in 3 dimensions, and that can be a little bit challenging because most of this course we've really been concentrating on doing things in 2 dimensions. And again, this is expressed a number of different ways. V cross B, again, F is represented by the direction of the thumb. This is actually true for any cross product. Again, another variation of this right-hand rule. So just for some examples, we'll take a look at this. We'll say that, let's say we don't know what direction the force is. The force is shown right here in red. Again, we're going to do V cross B. X is coming in this direction, Y is going in this direction, and Z is going upward. Here we have our velocity in the X direction. We're going to curl our magnetic field in the Z direction. So V cross B, and that gives us our force right there. Again, V cross B puts our force into the board right here. And in fact, in the lessons, we have quite a few of these different examples. Again, when velocity and magnetic field are in the same direction, there's no cross product. Theta is 0 and the sign of 0 is 0, so there's no force. Again, here we have it sort of at an angle, V cross B. It's going off in this direction right here. Let's take a look at a problem here. We have a proton moving with a speed of 10 to the 5 meters per second through the Earth's magnetic field. Now, the Earth's magnetic field is about 55 microtesla, all right, at a particular location. Let's say this proton's above the atmosphere. As the proton moves eastward, the magnetic field acting on it is directed straight upward. So we can imagine here's our Earth, north is going this way, the proton is moving eastward. What is the direction of the magnetic field? Okay, let me go back to this again because I messed up the original question. When the proton moves eastward, the magnetic force acting on it is directed straight upward. So reorient ourselves again. Again, this is why three dimensions is a challenge to think about. All right, imagine the screen, okay, is the surface of the Earth. North is this way, east, west is that way, upward is this way. So what we have is a magnetic force going straight up. We have the proton moving eastward, okay? So here's my V, okay? So only across B, a magnetic field pointing to the north is going to give me this upward force on the proton, okay? So here we're using a known magnetic force, which is our thumb with the right-hand rule. We're using a known direction for V, which is the direction of the proton, to calculate the direction of the magnetic field, or to determine the direction of the magnetic field. So that's A. What is the strength of the magnetic force when the proton moves eastward? We'll do that calculation. And then finally calculate the gravitational force on the proton, and we'll also compare it to the electric force if it were an electric field with magnitude 150 newtons per coulomb. And in fact, there is an electric field due to the polarization of the atmosphere, but we'll do that calculation also. Okay, so again, in this particular case, you know, we're looking at the direction. This is oriented a little bit differently. We have the velocity going this way. The magnetic field was actually coming out of the board. So, I'm sorry, again, this is east, this is north-south. I've got to get used to this right-hand rule myself. I only do this every other semester. I should be used to this by now. So it's even challenging for me. But again, we have V to the east, we have the force, which is upward, and then we do V cross B, that shows B heading northward. So this is oriented a little bit differently, where east-west is this way, south and north are this way, and up and down are up and down on the screen. Okay? Again, 3 dimensions is not easy to visualize what's going on. Calculate the strength of the magnetic field. Again, this is the full vector form, but if we want to reduce it to a magnitude, we can just write it as QVB sine theta. Here's the charge of a proton. Here's the velocity at which the proton is traveling. Here's the strength of the Earth's magnetic field. And of course, it's perpendicular. It's at 90 degrees, so the sine of 90 degrees is 1. We get a force of 8.8 times 10 to the minus 19 newtons. Okay. Calculate the gravitational force in the proton. Well, that's easy. We'll assume that the acceleration of gravity up there is about 9.8 meters per second squared. We multiply it by the proton's mass. We get a much smaller force. The force due to the magnetic field, 10 to the minus 19, is 7 magnitudes, over 1,000,000 times greater than the force due to gravity. So certainly the proton is going to be influenced by the magnetic field much more. Likewise, we can calculate an electric force where we're given an electric field of 150 newtons per coulomb. Again, F is equal to QE. We get that force is 2.40 times 10 to the minus 19 newtons. So the electric field actually would dominate the magnetic field here. Okay? So get a chance to do a calculation on a charged particle due to a magnetic field, due to the gravitational field, and due to an electric field, assuming 150 newtons per coulomb.